Before we move into general relativity and how it might inform our view of empty space, I think it would be worth rehashing just how the theory altered our conception from the classical picture. For our listeners who aren't familiar with Einstein's work, is there an easy way to describe the shift in space-time from the Euclidean absolute image of Newton's to one that's relative, that doesn't allow for absolute simultaneity and so on? And we don't have to be comprehensive at all because these issues have come up on the past in the show.
Yeah, so Einstein's work on space and time happened in two stages. The first one was really driven by foundational problems in Maxwell's theory of electromagnetism, having to do with precisely the kinds of things that Leibniz was worried about. So Leibniz is worried about the physical significance of absolute rest and what role determinations of absolute motion can play in Newtonian physics. Maxwell, on his own conception of the theory, of his theory, can be seen as sort of relying on a Newtonian concept of absolute rest. I mean, he's doing this by introducing a substance, that the ether, the luminiferous ether, the material through which light is supposed to be moving, and supposing that that's at rest, or at least is providing a standard of rest. But what people realized over the course of the late 19th century was that this state of rest, this luminiferous ether, whatever its state of motion was not playing any observable role in electromagnetic phenomena. And this led to some kind of deep puzzlement, because it seemed as if the theory required this. But it also seemed as if the theory needed to be our theory of matter needed to be like carefully tuned, almost gerrymandered to look like, have these like kind of conspiratorial features, such that we could not measure motion relative to this absolute state of rest associated with the ether. And so Einstein's idea is to sort of really go back to the basics and say we can get rid of this presupposition about the state of, this absolute state of rest and this ether by reconfiguring how we think about space and time. And what this ends up doing is, in the first step, just sort of changing definitions about what length means, what duration means, what angles are, making all of those quantities relative to different states of motion. So different observers in different states of motion, different measuring instruments in different states of motion are going to make different determinations of these quantities. The definitions of the quantities end up being relativized to idealized measuring apparatuses. If you redefine things in this way, the conspiratorial element goes away. You no longer need it to be the case that electrons are undergoing some complicated internal dynamics in order to make it impossible for us to measure the behavior of the ether. What's happening is that our conception of space and time is just different than we thought it was. What we mean by length is changing. Now, that happens in 1905. Shortly thereafter, it's recognized that by Hermann Minkowski, it's recognized that you can reconceive all of this in a very nice geometric way, where you can think of Newtonian spacetime as attributing a certain geometrical structure to the totality of events in space and time. You can see Einstein is just attributing a different, in many ways closely related, but distinct structure to the totality of events in space and time. But again, the basic thing is we're encoding information about lengths and durations. The final step comes, between 1913 and 1915, where Einstein is trying to figure out how to take this, very beautiful new geometric picture that makes sense of electromagnetism and fit in Newtonian gravitation, right? Because the beginning of the 19th century, the beginning of the 20th century, rather, we have these two theories. We have Newton's theory of gravitation, which is still doing a great job in virtually all of our applications. In fact, we have hundreds of years of precision tests of Newtonian gravitation. This is as well established as any theory could have been at that time. But then we also have Maxwell's theory. And Einstein has argued that Maxwell's theory requires this radical reconceptualization of space and time. But Newton's theory doesn't fit with his new conceptualization of space and time. And so you have this kind of tension, right? Is it the space-time that Maxwell's theory seems to need, or the space-time that Newton's theory seems to need? And so Einstein's idea is that we should reformulate gravity in a way that's compatible with relativity. And this is what ultimately leads to this idea that gravity actually isn't a force at all. Gravity is a manifestation of the space-time structure. And that the way in which you get all of the degrees of freedom you need to describe gravitational interactions is that space and time have themselves additional degrees of freedom, that space and time can be curved. And what we mean by space and time here is still, once again, the sort of encoding of the kind of measurement apparatuses, like the things that measurements can be made. Now, subsequently, we came to think of things in a much more geometrical way, where it's kind of these operational definitions, in some sense, fall away or come to have the status of interpretational principles or interpretive principles. But at least I think the way that Einstein was thinking about it, that kind of operationalistic picture was still very important to him as he was understanding what it meant for space and time to be curved in 1915. Was that?
Yeah. You said that one major consequence of the shift from Newton's view of space, among other major consequences, is how we conceive of length, and then perhaps by extension, no pun intended, distance. And in the classical picture, I mean, it's quite easy to make sense of distances and relations in space because we know how to do this in a three-dimensional or four-dimensional Euclidean space. But maybe to wrap our heads around space in Minkowski, who you mentioned, Minkowski space-time or Schwarzschild space-time, how do we even measure distances to pick out or describe intervals or volumes of space in the first place?
Yeah, so, I mean, let's just start with special relativity. The picture that emerges is one in which, so for Newtonian physics, there's a fact of the matter about the spatial distance between any two simultaneous locations, any two simultaneous events. And there's a fact about the temporal distance, like the amount of time between any two non-simultaneous events. Newton thought there was also a fact of the matter about the spatial distance between two non-simultaneous events. And this is ultimately, whether there's a fact of the matter about that question is the thing that is at issue in the 20th century resolutions of the Newton-Leibniz debate. In relativity, ultimately what you want to say is that you simply don't have those kinds of relationships. The relationships you have are spatiotemporal distances between events. And given any two events, there's a fact of the matter about the spatiotemporal relationship between them. There's some number you can assign. There's a metric that measures the distance between any two events in space and time. The thing is that when we talk about lengths, we aren't talking about space-time distance. We're talking about spatial distance. And so what we end up meaning by length in ordinary conversation, I mean, in a lot of physics too, but in ordinary conversation, is something that we have to kind of reconstruct within relativity theory as the sorts of things that someone who is trying to make certain kinds of measurements while themselves moving through space and time would end up doing and saying. And so measurements of length end up being a kind of derived notion, derived as like the projection of the space-time distance between two events, or the space-time distance really between two trajectories representing, say, particles undergoing different states of motion, or the edges of a ruler or something like that over time. The projection of that information onto something that observer thinks of as space at a time. Does that make some sense, or is that helpful?
Yeah. Very, very much sensible and helpful. One peculiarity about all of this that I wanted to make sure that I asked you about was not about Minkowski spacetime, but Schwarzschild spacetime. And how is it that it results in situations where two regions of space are no longer even connected? Or rather, I mean, we might think of it as there being no distance between them, as measured by the time it would take light to pass from one region to another.
Yeah. So, I mean, this is how we represent black holes, right? I mean, there's, I think it's pretty common. I mean, both among astrophysicists and among people who aren't like, neck deep in general relativity, to think of black holes as like, compact objects just out in the world, kind of like stars, but just kind of denser. But given the relationship between gravity and space and time and general relativity, you end up with a situation where what's distinctive about the interior region of a black hole is that there are no paths that light or any massive body could travel to get from the interior of a black hole to the exterior of the black hole. There's no trajectory you can follow that would take you from that place to that place. Now, time in general relativity isn't absolute, right? You give me two events. It's not the case that I can say how long, like what the duration is between them. What I can do is, if they're related by the kind of path that a massive particle could follow, I could say how long that particle would think it took to get from the first point to the second point along whatever path it traveled. And so, what I can do is I can say, like, I'm trying to think of an example of like some specific historical event, and the thing that's coming to mind is like the magic bullet from Dallas in 1963 that killed Kennedy. Okay, but like that thing has followed some trajectory to where it is now, and what general relativity can tell you is how much time that has measured, but it's measuring it along a particular path through space and time. And if it had taken a different path through space and time, it would have measured something else. Okay, so now coming back to Schwarzschild spacetime, the key thing is what we mean by duration is only relative to the sorts of paths that massive bodies can follow. But the interior of a black hole is such that there is no path out. There's no way to get out of it. There's no path that can take you that like along which this kind of measurement could be made, which ends up having the consequence that regions in the exterior regions of black holes, like places outside of black holes, are not before or after. Or there are some that are before, I guess, but there aren't like locations outside of the black hole that are, after any region inside the black hole. You get this kind of radical disconnection between the interior of the black hole and the stuff outside for this reason.
Now, Newton's view of space seemed to provide a much more intuitive picture of what nothing, or before I say much more, it provides a very intuitive picture, I think, of how we should think of space when there are no objects in it. But it's not as easy for me to do the same with these revolutions that came from Einstein, particularly because, for instance, in the example we just gave with black holes, it is a massive object that gives space these distortions and very salient properties. So how is it just that we have to think that there must be this pre-existing or object independent geometry to space without objects, that these massive objects warp or that light travels along? This is how we should think of space in the absence of anything?
So first on the intuitive picture, I mean, there's something I completely agree with you, of course, but I think that there's a kind of historical accident here, because Newton's views were considered extremely counterintuitive, right? Leibniz was defending the default view. Descartes and all of these other philosophers, in the 15th and 16th century, would have endorsed, relationist type views. And so there's something kind of odd about saying, well, but Newton's views are so intuitive to us. Like, they really weren't intuitive at the time. I mean, they're intuitive now, maybe for reasons having to do with like enculturation and custom and stuff like that. Like, we're taught to think about space and time in largely Newtonian terms. Our first introduction to physics is invariably through Newton. If when you're a little kid, your parents don't tell you, oh, like, when you drop that, it's going to fall because of gravity. They tell you instead, when you drop that, it's going to collide with the Earth because you're no longer exerting a force to keep it up. Maybe you'd end up having different ideas about space and time. I don't know. I'm not trying this experiment with my kids for what it's worth. So I think the thing to say about it seems to me like what you're worried about with relativity is how to think about these situations where you have curved space-time but no matter. Are we in some kind of weird modal space where we're considering situations where matter is curving space-time, but we've imagined the matter isn't there, and so now we're in some kind of counter nomological, non-law governed situation or something like that. And that's not actually what is happening here. The thing is that general relativity, like Einstein's equation, the fundamental equation of general relativity, the equivalent of Newton's, kind of the equivalent of Newton's law of universal gravitation, allows for solutions in which there is no matter, but space and time are curved. I don't think this is exactly the right way of thinking about it, but one idea that physicists sometimes have is that because this theory is nonlinear, there's a sense in which the curvature of space-time reacts to itself. And so there's a kind of space-time being curved leads to curvature of space-time, right? And so you end up with this kind of self-consistent totality, but where you don't need an entity that's causing it to curve. It's sufficient to have curvature that you just have a kind of a global solution in which curvature is present. You don't even have to think of it in terms of global solutions, actually. You can give me some initial data. So specify the world at a time. And suppose that in that world, there's a little bit of curvature. There will continue to be curvature. It will evolve over time in such a way that curvature is going to, have other effects on the curvature of space-time. Maybe the most intuitive cases. So black holes are a weird case because we want to think of black holes as things. They're the remnants of collapsed stars, stuff like that. But general relativity allows for a possibility where there was never a star in the first place. You just have, globally, infinite, from t equals negative infinity to t equals infinity, a black hole present with no matter anywhere ever existing, right? And if you imagined what it would be like to be, a little speck of dust in this otherwise empty universe, you would gravitate towards this thing. You would approach it as if it were a planet or something like that. But there's no stuff there. There's just the curvature.
Right.
But I think the most intuitive kinds of cases are to think about gravitational waves. Right. And so so think about a situation where you have like, well, so, I mean, as a first step, think about like an incandescent light bulb where you have some current running through a resistor. The resistor is getting hot and it's releasing photons. And then the photons are sort of propagating away from that, excited object. Now imagine a situation where instead of running a current through a wire, you have like, a binary star system, and these things are orbiting each other, but they're orbiting each other in some sort of way that ends up producing something analogous to electromagnetic radiation. And just like the electromagnetic radiation will sort of travel away and then, eventually hit your retina, these gravitational waves will travel away from that rotating body. But as they're traveling away, they're in a region where there's no matter, right? So, I mean, you've got these two things that are going around each other. They're sort of emitting this gravitational radiation, but far away from them, it's just the radiation, the gravitational radiation, which is all curvature, propagating under its own speed or under its own momentum, I guess. Now, we can detect those, many, many, many light years away. But so you can imagine a situation now where you're in that region of empty space, and all you have is the gravitational radiation, sort of the relic from this this binary star system far away from you, introducing curvature, like dynamically moving, introducing curvature, like over time through this region of space where there isn't any stuff. Now, the final step is to say, well, now imagine that the universe just consisted of that empty region. You just have, curvature undergoing some kind of dynamics as described by Einstein's equation in a wave-like state without any matter present at all.
Yeah. Well, before we finish with a bit about quantum field theory, here's what I think of as more squarely a bona fide philosophical question. Does this picture of space in general relativity, where space has its own geometry that warps and ripples with gravitational waves or with black holes, does it strike you at all as something bordering on Platonic in the sense that it gives an existence to mathematical objects? Maybe, one response is that if it's causally efficacious, it's not Platonic and is, just definitively physical.
Yeah, I think just consider like how easy it would be to solve the Nassar's problem if you could set up two mirrors a certain distance away from one another and then detect the number 2 in the wobble between the two mirrors, right? Yeah, I think there are lots of things that you can say about the relationship between mathematics and physics and the sense in which math is the sense in which we're taking mathematical structure and attributing it to the world and what that means. But ultimately, what general relativity is telling us is that the physical world behaves in certain ways, and that stuff is causally efficacious, just as you say. It results from other kinds of physical processes, and it influences other kinds of physical processes.